Okay, you won't be able to really see it when I rotate this thing in a horizontal plane. You kind of got to use a horizontal plane because we get some rotational friction in here if I don't. But there's a nickel on this thing. And then I rotate it and speed it up and speed it up and speed it. And there goes the nickel. Fell off. Why? Well, we talked about it. And we figured that apparently it takes some force to hold the nickel on here. Okay? And we conclude that the force is not in this direction or this direction when this thing's rotating. Because if there was a force in this direction, well, the nickel, there's a gravitational force, there's a normal force. They're in balance. So if we had a friction, the net force on that nickel then is just whatever frictional force there is between the nickel and this magnet. And that frictional force between the nickel and the magnet can't be in this direction or this direction, because either way the nickel would be speeding up or slowing down. And obviously we could do this at a constant angular velocity. When we crank the constant angular velocity up far enough, the nickel's going to slide off, as you saw. So we conclude that the force has to be along this line, either this way or this way. Well, the nickel slid this way. Friction exerts a force in the direction opposite motion, so the force has to be in this way. It has to be back toward then the center, the axis of rotation, and that's totally consistent with this picture from the videos I made last time. Okay? Where these are your velocities, tangential velocities of something, that nickel moving around the circle. Okay? And the picture of the circle would be like this, and the velocities are here around the circle, tangent to the circle. We take those velocities, we put it in the diagram, we have this. So between any two velocities, if we're moving at constant velocity, the two velocities and the vector difference between those velocities form an isosceles triangle, and that isosceles triangle, the limiting process, leads us to the conclusion centripetal acceleration is v squared over r, and I expect everybody to know that argument. Okay? That was totally accessible. That may be a little harder than it was for my generation because nobody knows much geometry. Yeah.
Sorry to bother you.
Yeah.
I just want to see if I can come in
Help
and fix
yourself.
your air conditioner right quick.
You won't bother us a bit.
Thank you.
Yep. Okay. Okay. Make sense? Okay. So there's your centripetal acceleration, and of course then by Newton's second law, the centripetal force that force is mass times acceleration. And this says that you have a net force for any object in uniform, moving with speed v on a circular arc that's equal to v squared over r, where r is the radius of that arc and v is how fast it's moving. Okay? That is the net force. It can't be moving in that circle unless it has this net force. Okay, this centripetal force and all other forces add up to nothing, add up to zero. They balance each other, totally in balance, except for the centripetal force. Okay? And that's you in a car going around a curve. Same thing. The friction on the seat, or whatever mechanical, you got your feet on the floor, your brace, whatever. Okay? All those forces are there to balance the centripetal force. Okay? So centripetal force is trying to pull you in. Well, you got to push on the steering wheel this way, or friction has to exert a force in this direction. All that stuff. And of course, the tires in your car have to exert, the road has to exert enough force on the tires in your car to keep you in that circle. Okay? And that's friction. Unless you're laying rubber, in which case it's also material force. So, make sure you understand as much of that as you possibly can. It'll be very useful to you. Okay?